All right, welcome to day 37 of GL001. All right, we're almost to the end there. Can't believe it's been 37 days. And just some logistics for this week. All right, what you have due on this Sunday night at 11:59 p.m., April 26th, is the lecture quizzes from this week. So day 37, 38, and 39. Lab 10, which is a pick your own geologic topic and make a creative presentation about it. And I promise that this is shorter and easier than Lab 9, okay? And I will be sending out a separate email with directions about what you need to do for this, okay? And then this is a change from the syllabus. You will only need to read Chapter 8 this week, okay? And that's the one about earthquakes, all right? So then we should start looking forward because soon we are about to end this time warp of a semester, and it's almost the end of classes. So this is the second to last week of class, followed by next week, okay? After Lab 10, there will be no more labs, okay? And then you should think about the final. And we can talk more about this later on, but I wanted to make sure that you started thinking about it. It'll be similar in how it's administered on Blackboard. Might be a little bit more challenging than the last one. Not too much, but the main thing that I want to say is that you will need to take it on May 7th, okay? I will not have like the 2-day window. We're just going to do it on one day. And we'll talk more about the details for that in the future. So just add that to your calendar. You should already have that in there, maybe because of how the semester was supposed to go originally, but please add it into your calendar. And if you have something going on the 7th, like I know we all have really different schedules right now, let me know so I can figure something out with you, okay? All right, so let's jump back into the rock cycle. So after last week with our little interlude with flooding, we were talking mostly about Dwayne the sedimentary rock Johnson. Now we're going to go to the last piece of the puzzle that we have not talked about in this class yet, and go to metamorphic rocks. So truly, we're going to be asking, can you smell what the rock is cooking? Because we'll be talking about how the application of heat and pressure through burial in Earth's crust and upper mantle can transform rocks, okay? So metamorphism, right? So let's just split the word up and define it, right? So meta is Greek for change, and morpha is Greek for form. So metamorphism means changing form, a rock that has changed from its original form. All metamorphic rocks have a protolith. So the proto is like the prior existing, lith means rock, the rock that was there before. And remember that from what we know in the rock cycle, the protolith for a metamorphic rock can be sedimentary, it can be igneous, or it can be another metamorphic rock, right? What we have with metamorphism is solid state transformations. This means that you are not actually melting the rock down into a liquid, right? If you did that, you would be creating a magma, and then it would be an igneous rock. Metamorphic rocks have to remain in the solid state. So that means you're seeing chemical and physical changes that do not leave the solid state, all right? And then how do we accomplish metamorphism, right? So we can do things like bury it under a ton of sediment or other rocks. We can apply heat to it, like if it got close to a magma chamber. We could apply even more pressure if you put it at like a tectonic convergent zone where you have a lot of stress. And the application of stress is just forces acting on that rock, right? So like, imagine if we've got Meta World Peace here making a metamorphic rock, if he exerts pressure onto the basketball, right? He's exerting stress, right? Ultimately, with metamorphic rocks, we create new rock types through the application of heat, pressure, and stress. Okay? So let's talk about protoliths in like the simplest example possible. Okay? So our protolith is limestone, right? Calcium carbonate, the rock that fizzes if we put a little hydrochloric acid on it. Let's say you have a intrusion of magma beneath the subsurface that bubbles up, and because of the heat from that magma chamber, it is causing contact metamorphism, right? It's baking that limestone. When that limestone bakes, it creates marble. Marble is still calcium carbonate, but it is the metamorphic form. Okay? So if we looked under a microscope at a fossiliferous limestone, a limestone composed out of like little shells, right? You might see all these biologic structures, right? Like shell fragments. After that contact metamorphism, you heat up and change the structure of that rock. You haven't completely melted it, but you have heated it sufficiently that those mineral grains have changed in shape. Okay? So what is a metamorphic rock? Okay? So we can define this in a couple of ways. The first is the types of minerals, right? Certain metamorphic rocks only have certain types of minerals. And there are minerals that only form in metamorphic environments, okay? And when you pick up a metamorphic rock and you look at the specific minerals that you find in it, that defines the type of metamorphic rock you have. So for example, on the right here is a picture of a chlorite garnet schist. Okay, the sort of green, waxy colored smaller minerals is a mineral called chlorite, and these dark ruby colored minerals are called garnets. Okay, the other important way to define a metamorphic rock is by its texture. And the texture is really the like manifestation of the arrangement of mineral grains. So this can be things like foliation, like a schist, right? You guys have, if you've gone like up to the Mad River Valley, like you've gone to Sugarbush or Mad River and gone in one of the swimming holes up there, and you look at the rocks that are, in the riverbed there, there's a lot of schist, and you can peel away little fragments of rock on there. That's the foliations. That's the texture of that schist. Okay? So now let's talk about metamorphic processes. Okay? What happens to create new rocks from other protoliths? Okay? So we can have a few things, right? We can have recrystallization, right? And this is when you have it change in the shape and the size of grains, but the mineralogy remains the same. Okay, so if we have like little quartz crystals, right, like maybe in a quartz sandstone, and you put it under enough heat and pressure, you start to meld all of these together and stretch them out into these more stretched out quartz grains. Another one that you could have is metamorphic reaction or neocrystallization. This means that you are forming a new, completely different mineral. That means different chemical formula and crystalline structure from a protolith. So with enough heat and pressure on clay and quartz, you can create quartz, garnet, and mica. Mica being like biotite or muscovite. Another process is pressure solution. So as the protolith undergoes metamorphic conditions, heat and pressure, you may dissolve certain parts of minerals, right? Just like pressure melting with ice. If you put stuff under enough pressure, you can cause some dissolution of minerals, okay? And as that happens, it can cause sort of like lubrication within that rock body and form new minerals and new shapes. And then finally, plastic deformation is where you heat rock up high enough that it still remains a solid, right? But it is at such a high temperature and or pressure that it begins to deform or move like plastic, right? It's no longer rigid or brittle. It can kind of flow, right? So initially, if we have some protolith that was rigid, and then you put it up to conditions where it can flow plastically, it begins to shear and sort of elongate grains into elliptical shapes. Okay, and then one more is phase change. Okay, so this is one that's really important for metamorphic rocks. This is where you can have the exact same chemical compound, right? But under specific heat and pressure conditions, you rearrange the crystalline structure. This creates what we call a phase change or a polymorph. Okay? And that's really just the rearrangement of atoms in the crystalline structure. And as we know from back in that mineralogy unit that we did, when you change the crystalline structure of a mineral, it is manifested in different colors and different crystal habits, right? So one that, just to show you as an example, Al2SiO5, it's an aluminum silicate, has 3 different forms it can take on under varying pressure and temperatures. At low pressures and relatively low temperatures, we have a rock called andalusite. At high temperatures and high pressures, it can turn into a different mineral called sillimanite. And at high pressures and relatively lower temperatures, you have the mineral kyanite. So, right, just like in the Spider-Man multiverse, you can have many of the same thing existing that are ultimately the same, right? But they look different, okay? So that is just another way that metamorphism can proceed and create new minerals, okay? Right, so what triggers metamorphic processes? When we think about it, it really comes down to just a few things, right? Heat, right? The interior of the earth is hot, it gives us heat. Pressure, the weight of rock. Right? Stress, being sort of pushed in different directions, pushed and pulled. And hydrothermal fluids, the movement of hot water through the system, okay? And I didn't think that I would ever be able to find a GIF that perfectly summed up all 4 of these things in one image, but here we are. All right, so let's talk about heat and pressure, okay? So when we heat up rocks in metamorphism, we cause a solid state diffusion. This can result in a morphological change, meaning that the shape of mineral grains will transform in your rock. But ultimately, you're not changing the actual mineral, right? Just the shape of it. For metamorphism to occur by heat, you need temperatures that are in this Goldilocks zone, right? Between 250 and 850 degrees C. If it's lower than 250, nothing's going to happen. It's too cool, right? If you get hotter than 850 degrees C, you melt the rock entirely and you form magma, right? So you need to be in that temperature range for metamorphism by heat to occur. Pressure. So how do we get pressure in the Earth system, right? It's the weight of overlying rock above. That creates a pressure on the rocks below, okay? This is kind of difficult to think about at the global scale. So what I recommend is thinking about when you're going swimming, okay? When you get in the shallow end of the swimming pool, right, you just kind of feel the water around you, right? But it's not painful if you stick your head underwater when the water is only about 3 feet or a meter deep. But if you go down to the deep end of the pool, where the depth of the pool is like 12 feet or about 4 meters, right? And you go all the way down to the bottom, and you try to sit down there and hold your breath, you can feel all the pressure of the water around you, and you feel it in your ears, right? You are feeling the weight of the water on top of you and around you exerting pressure onto you. The same principle applies in the earth. As you put a rock further down into the crust or even into the upper mantle, the more pressure it's going to feel from the weight of rock above it. Okay? By changing both temperature and pressure, we create metamorphism. Okay? Right? And so these two graphs here are showing how temperature and pressure change with depth from the surface of the Earth towards the inner core, right? This shouldn't be a surprise. The inner core of the Earth is hot, right? So we have a geothermal gradient, right? The geothermal gradient is actually less steep near the outer part of the Earth, right? Near the crust and very uppermost mantle. And then, or actually it's a more steep geotherm, sorry. It gets hotter with not a whole lot of depth, and then it drops off, right? There's not a lot of change of temperature with a large change in depth, okay? And then we have certain jumps, and these jumps are caused by chemical differences in the Earth's interior. But pressure, right? We have mostly, almost a steady increase in pressure with depth, okay? And that's because of that overlying weight of rock above you. Right? Okay, so heat and pressure can transform rocks, but the other important one here is stress. Okay, I'm not talking about like stresses in like schoolwork. I'm talking about stresses in being put under force or under a pressure, right? So we have two main types of stress we'll talk about here. Together, they result in what's called differential stress. That means that you have unequal application of force on an object, basically pushing and pulling. So a normal stress or a compressional stress is one where you have pushing down, right? Like perpendicular to a surface, right? My fist is compressing onto my palm, okay? That causes compression and underneath my fist, and it causes tension up in the 90-degree angle away from it. Shear stress is the application of force parallel to a surface, right? So now I am trying to move my hand along my palm, right? I'm applying a shear stress. The result of applying compression and shear on rocks is a preferred orientation of grains in the rock, right? So when you heat up and apply pressure onto these rocks, right, you are going to basically roll out elongate or platy minerals, okay? This is what gives us rise to things like foliations and schist, okay? And then the last process that can trigger or cause metamorphism to occur is the migration of hydrothermal fluids. So hydrothermal fluid is just really hot water that's carrying dissolved minerals or ions through it. The incredible pressures that are going on in Earth's interior allows this water to gush through fractures and conduits in the rocks. And as that water passes by, it causes chemical reactions and metamorphism. This process of hydrothermal alteration and metamorphism is extremely important for mining. This is the process by which most precious minerals and rare earth elements are formed. So things like gold, silver, copper, nickel, cobalt, mercury, lead are often formed through hydrothermal alteration. Okay. Flip side of that, though, is that those same minerals are also extremely dangerous to humans and hazardous to basically living things. But so this is hard to visualize going on inside the interior of Earth's surface, but we have hydrothermal activities going on near the surface in geysers. So this is a video of a slow motion eruption of a geyser in Iceland. This is a really weird another weird show that I found on the internet, but we're just going to fast forward to the part that I thought was good. Okay, so they've got a drone, right? And they are flying above this small outlet of a geyser, right, where the pressure is released and it causes a gushing of hydrothermal water or hydrothermal fluid to flow out. Okay. So you can see that when you put this liquid under intense pressures, it flows very quickly. The other important thing to note here, right, is the change in color of the surface. Right? The change in color here is a hydrothermal alteration because you have that hot mineral-rich water that's flowing out onto the landscape and causing chemical reactions with pre-existing rocks. Okay. All right, so different rock types. We have one foliated metamorphic rocks. All right, so a foliation is a thin sheet that is formed through preferential stress, heat, and pressure. Okay. As you increase the heat and pressure, you cause additional metamorphism and changes in metamorphic foliated rocks. So it's about lunchtime, so why not think about paninis, okay? So basically a panini maker, right, like the George Foreman grill, it's hot and you press stuff, right? So heat and pressure, right? So you can watch as your panini goes from being shale, right? That's the protolith, right? Nothing has changed in terms of pressure or temperature. And as you apply heat and pressure, you flatten out and bake and melt certain ingredients first. And then eventually, if you put it on too long, too high of temperature and pressure, you melt the whole thing and ruin your sandwich. Okay? It's just, now let's talk about the specific rock types, right? So again, as we increase temperature and pressure, you cause metamorphic processes to occur. When you make a panini, you basically cause certain ingredients to melt first, right? The bread might toast. If you have some cheese in there, it might melt earlier than like the meat that isn't going to change as quickly. But eventually, things all start to change towards the end if you leave it in the panini maker long enough. So the progression of foliated metamorphic rocks starts with shale, then goes to slate, to phyllite, to schist, to gneiss. Okay, that is the sequence. The ultimate protolith for gneiss is a shale. Each of these preceding rocks, right, is the protolith for the next. Shale is the protolith for slate. Slate is the protolith for phyllite. Phyllite is the protolith for schist, and schist is the protolith for gneiss. Okay? And then finally, we have non-foliated metamorphic rocks. So these are ones where we do not have the thin sheeting that you can see like in schist. And this could be the result of a lack of compression or shear stress on that rock as it was metamorphosing. There are three types that you need to worry about. There are hornfells, quartzite, and marble. Hornfells can form from a variety of different protoliths. Quartzite forms from quartz sandstone. You go from having like individual sand grains that you can see to they being recrystallized into larger quartz grains, and it kind of looks like sugar candy. And then marble, right? We talked about that at the beginning of the lecture today, but that is initially formed from limestone or dolostone, right? It's made out of calcium carbonate, and then you heat it up and you turn it into marble. And Vermont is very famous for its marble mines around in the Green Mountains, and many of the main monuments in Washington, D.C. were built out of this building stone. So Wednesday, we'll talk more about metamorphic environments, okay?